Hey guys, so today I'm going to do a little weekend project with infrared. So I just got back from Radio Shack, picked up a couple of these emitter and detectors, and also I picked up a couple of these 38 kilohertz pre-tuned receiver modules that should handle the demodulation for us. So I haven't really messed with infrared much in the past, so I'm going to hook both of these up to the oscilloscope. We'll point an infrared remote control at it and kind of see what the raw signals look like from both modules. Alright, so this is the game plan. For the infrared detector, I'm just going to use that to bring 5 volt through to our probe with a 10K pull down, and then for the receiver we'll just hook that basically direct to power and the probe. I've got my breadboard with some stuff on it already, which is nice because we'll probably end up using the microcontroller a bit later. And let's go ahead and plug in the circuit. Alright, you can ignore if these lights are blinking and stuff. I've got a little test remote here, and I'll go ahead and just fire some infrared at it and we get response for sure. The yellow is the IR receiver, and red up here, which might be a little bit hard to see, sorry, is the photodiode. So as you can see, it doesn't really matter where I put the remote. We get the same strong signal. These are the same 1 volt time division, or vertical divisions, by the way. But the infrared photodiode is like really weak. At least from here you can barely see it. If I go right up on it, then it definitely has better strength. But yeah. So anyway, let's actually take a look at the modulation or demodulation capability of the IR receiver. So I'm going to turn my time division in. Let's fire another shot here. You can get a good one there. Let's go a little bit more. It's a little bit hard because it's walking around, but let's see if we can set up the trig menu for, say, single. There we go. That's not bad. So you can very clearly see that you get a lot of signal here, a lot of bouncing up and down, and just a straight drop off. Let's see if we can go into one of those in more detail. So there is our 38 kilohertz signal at the top, and effectively demodulated by the infrared receiver. So anyway, definitely not going to use the infrared photodiode. That just looks like a pain in the butt to deal with. Definitely could, but I like this receiver. Let's set our trig mode back to just auto, and let's see if we can start decoding some of these signals coming out. Alright, so I'm going to try and start kind of decoding this signal and see if we can make a differentiation from one code to the other. Again, this is that initial burst, and then after this burst we get these like repeating signals. So I don't think that those really matter. I think it's the initial one that we really care about. And there's quite a bit going on in here. So one thing that I haven't done that I want to make sure I do is to do a comparison with another remote. Totally different brand, Yamaha versus Samsung, whatever, just to see if the overall kind of protocol looks to be about the same or not. So this is going to be the Yamaha. Fire another one off. I'm going to save it. Waveform saved. I'm going to turn that on. I'm going to slide the live trace down to the bottom half. So top half is going to be the Yamaha, the bottom half is going to be the Samsung, and that was, I think, the up arrow. So I'll do the same. I'll do an up arrow on the Samsung as well. And here we go. Okay, it's similar. It's not the same. It does have that front porch, or whatever you want to call it. Let me just fire another one here. Does have the same initial you know, active, inactive, and then it pulses out the thing. And it's actually pretty much the same bit code length, I would say. Like the whole message is about the same length. I think probably they are basically the same. Maybe the only difference is the actual clock frequency is different. That's interesting. I'm going to find another remote and do a third comparison. Alright, so I've got a third remote now. I've also saved both the other waveforms and shifted things around a little bit. So the Yamaha is on top, that's the up arrow. The Samsung is in the middle, that's also the up arrow. And then I've got my Logitech Harmony remote that of course doesn't go to a specific device, it's programmable. So I'm not even sure what the up arrow is going to try and target. It might do nothing because I have no activities active, but anyway, let's see what happens. Yeah, nothing. Okay, let's see here. Let's emulate an Xbox command. Not an up button, but you know, whatever. Let's see. Okay, these are all the same time division. That is, I would say, sufficiently different. Interestingly enough, it also has that initial drop-off, so I don't know. I mean, I guess infrared itself doesn't really have a protocol. I'm sure there are some standards. So I decided to take a break from the experiments and do some research, and consumer IR seems to be kind of the all-encompassing concept for all this stuff. It includes also IRDA, which we're definitely not looking at right here. In this page, it doesn't really seem to indicate specific protocols. I mean, it does, but you know, they reference like RC5 and RC6 stuff from Sony and Philips, and reading into those, you know, gets pretty complex pretty quick. And they do, however, mention NEC CIR protocol. Actually brings up some pages that have exactly what we're looking for. This is almost exactly what we were seeing on the traces before. And in fact, later on, they talk about repeat codes, which also looks very, very familiar. So I feel pretty confident that this is what I need. Looking back at our oscilloscope traces, I would claim that probably all three of these are the NEC protocol. That was the Yamaha receiver, the Samsung TV, and the Xbox. The only thing that kind of concerns me is that they are all different lengths. And that concerns me because at least this document talks about a very specific 9 millisecond leading pulse and a 4.5 millisecond. That kind of concerns me, other than the fact over here that the little subnote says that 9 milliseconds is 16 times the pulse burst length used for a logical data bit. So I'm kind of wondering if you're able to have, you know, your device measure how long this you know, width is, and then divide by 16 to come up with sort of the baud rate. But the actual protocol itself, the packet structure, is really simple. You've got kind of that front porch, and then 8-bit for address, 8-bit of just the address bits inverted, 8-bit command, and 8-bit command with the bits inverted. You know, so these inverted sections don't really provide any new data. It's a way to checksum and make sure that you know, the whole message is not corrupt. And before I forget, I did find another remote. This is from my Canon camera, and I would say it's definitely not following the NEC protocol. Alright, so over here on the left, I've built up a schematic of what's on the breadboard right now. So there's already a PIC16F 690 on there, along with red, yellow, and green LEDs. There's a red power indicator LED, a programming header for the microcontroller, and then we've added these items, the infrared detector and the actual full-out receiver. So I'm not going to use the infrared photodiode, so we're going to delete that. And I think we're going to connect the IR receiver to RA2. If we look over here on the datasheet for the 690, RA2 has not only interrupt on change, but also a dedicated external interrupt. And I'm not using it for anything else, so I figure why not. So we'll go ahead and slide that over. That should basically cover that. For driving the infrared emitter, got one over here. I guess we'll probably end up doing it from the C port. Those are all outputs already. But I got to figure out how much power we actually want to drive this thing. On the little back of the bag from Radio Shack, these are the specs. Of course, I don't have a real part number, manufacturer, and data sheet, so I'm going to rely on just this info. Instead of going to a full 100 milliamps, I'm going to derate it a little bit. We'll probably target 75 milliamps. So 330 ohms on our output. And we calculated roughly 44, we'll just say, I think 47 might be a standard value. That's going to be a problem though. I think all of the resistors I have are quarter watt. So I think we'll split this amongst two. So I think that's the final circuit design that we're going to do. This is the firmware for the chip. It's not running right now, but I have everything all hooked up and ready to go. I've done a little bit of work already. Actually, most of the code from this is from the previous firmware that was on the chip. But I'll go through it just real quick. Setting up the configuration. We have a interrupt service routine to keep track of total milliseconds for our sleep function, which is down here. Also in the interrupt service routine, I've kind of set up the external trigger for RA2, which is our infrared receiver, but I'm not doing anything with that yet. Let's see, I've got the old functions for just turning on and off the LEDs, and then I've got some inline assembly to handle the infrared emitter. So I've already played around with this a little bit, added and removed some knobs just to get the frequency right. But basically we just turn on the pin, wait a little bit, turn off the pin, wait a little bit, and then keep looping until our count runs out. And we're not using analog to digital, so I've disabled that. And then here's our actual main function where we just set up all the config stuff. I'm running at the default 4 gigahertz, so a 1 microsecond instruction cycle. A, we're not using, well, everything's input on A, that's the receiver. B is not set up currently. C is, as we saw in the schematic, all of the outputs. And the USART and the analog are disabled for now. I'm enabling all the interrupts for timer 0 and for the external interrupt. And then here's our main loop. So I've already tested this, but I'll run it again here. Re-enable this code. So it's going to do 8, 8, and 8 pulses and then sleep for 10 milliseconds and then just keep doing that. So let's go ahead and run this. Program the device. And here we go. So it works, and in fact actually I've got the frequency pretty darn close to 38 kilohertz. I don't know why it's jumping around a bit, maybe the trigger, I don't know. But the infrared receiver is definitely picking up on that, despite a little bit of instability in here, kind of between those 8 cycle sets, and I'm pretty sure that's due to the sleep, or the interrupt for the timer 0. So if I just turn off global interrupts and turn it back on after we do our pulses, and whoops, and program that in there, then we'll see that it cleans up quite a bit. And go ahead and pause that a sec. So it's not 100% perfect. Sorry, again, it's red. It might be kind of hard to see, but we get our 8 cycles, and then there's a little bit of an extra delay when it's like, resetting the 8 and making the function call and whatever. But definitely this receiver is picking up on it no matter what, and presumably anything else would too, which we will test. I've done a bunch of stuff off camera just to see if I can make this thing work, and I think that we're in a pretty good position. Originally I was going to use timer 2 and try to do all the reception in the interrupt service routine, but I switched to just using timer 1 and detecting the falling edge to start a timeout. So after 85 milliseconds, we're going to kill any reception, just to make sure that we don't catch like the back end of a message or anything. Anyway, if we go down here a bit, let's actually go all the way to the main function. So all it's really doing is trying to receive a message, and if it does, then it will send out through the serial port. I've added an RS-232 connection onto the board here. So it'll just send out to hyperterminal what it received, and that's basically all the main function's doing. If we go up to the actual receive message function, it basically disables all the interrupts, everything except for timer 1, just so nothing interferes with it, and then calls the internal receive message, which is up here. And basically, when the falling edge is detected, it stores the timestamp, and then by the time the main function catches up and starts processing it, we measure how long that whole transition took. And if it's longer than 10 milliseconds, which should only be about the 9 milliseconds here. So if it's longer than that, we're probably in the middle of a message, and we ignore the rest. Otherwise, we wait for this edge here. So our voltage logic is inverted, so we actually wait for the rising edge. But anyway, and then we time how long this period is open for, and that's done right here. We count the number of ticks. I found that 4.5 milliseconds is about 200 ticks, and that would be for a message command. And then for a repeat code, it's half of that time. It's a 2.25 millisecond space, which I found to be half of 200, which is about 100. If it's a lot longer or a lot shorter than that, then we might be in the middle of a message, or it might be a different protocol altogether, so we ignore that. And if it is a repeat code, we just store what the last message was and send that back out. So there's no special indication that it was a repeat. You just get the same message back. So if it is a message code, we come into here, and so at this point in time, we are on this edge, the start of a logical burst. And if you notice, all of these logical bursts, the top, the rised up part, they're all the same length. That's 562.5 microseconds. So regardless what data bit it is, they're all the same length. So we just basically wait for that signal. We make sure that signal is risen, and then we count how long. Sorry, we let the signal fall. We actually wait for it to rise because it's inverted again, but we wait for it to fall, and then we measure how long that space is in between. So for a logical 0, it's the same width as the burst, so 562.5 microseconds. For a logical 1, it's like 2 or 3 times that. I think 3 times that. It's 1 point blah 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 milliseconds. So we just count how long that inactivity period is, and I found that 76 millisecond ticks seems to be the logical 1, and 23 is logical 0. So, within some range of error. And these get pulsed out least significant bit first. So I'm keeping the, in the buffer it's going to be 0, 1, 2, 3 for the bytes, and I'm just handling the LSB to MSB swap as we go. So if it's a logical 1, I set the high bit, and prior to that we handle our shifting. That's everything. So let's go ahead and program this in and actually see what a couple commands look like from our various remotes. Alright, so we're programmed, and we've got our ready message in hyperterminal. Let's go ahead and let's say the Samsung remote, we'll just fire off a button at it, and there we go. We got a message. One interesting thing with the Samsung remote is the first 2 bytes, which should be the address and the inverted address, they're the same, which is really strange. So they might be using the NEC extended protocol, wherein the first and second bytes are actually an extended 16-bit address. I don't know, but anyway, we got the command byte, and the logical inverse is definitely correct there. Let's go ahead with the volume down button, and sure enough, the address is the same, but the actual command is different. And we can try a couple other buttons, and we'll notice the address is always the same, and the command is always different. So that works. Let's go ahead and try the Yamaha remote. So here's one totally different address, and actually the Yamaha remote does use the address and the inverted address, and then of course with the commands and everything. And one other interesting thing, if we can look at the oscilloscope, is the Samsung remote does not use repeat codes. They resend the same command over and over and over, whereas the Yamaha remote does actually use repeat codes. So we can see it's locked in at the repeat code there, but a single press, of course, just sends the full message. So that was one interesting thing. I noticed also, like, one button on this entire thing, the USB button, if we look at the command or the address, it's a different address, and it doesn't seem to follow you know, the logical inverse. I mean, it almost made me wonder if I had my LSB MSB thing not correct, but for other commands it does work. So I'm not sure what exactly is going on there. It's kind of strange. But anyway, that's those. Now let's try the Xbox remote, which should not trigger anything. And sure enough, you know, nothing's going on the screen here. So it's filtering out non-compliant protocols, which is good. Alright, so I think we're in a pretty good position to receive messages, and I think now we're also in a pretty good position to send them as well. So a few minutes earlier we took a look at this pulse emitter code, and I've now added this send message function, which accepts the front porch length as well as the command buffer. The reason being is because I noticed on the Yamaha it does use a 9 millisecond front porch, but the Samsung looks like it's either 4 or 5 milliseconds. So I wanted the ability to specify which one. So anyway, before we look at that in more detail, let's take a look at the main. The buffer I'm sending is just an alternating bit pattern. Like if you were to look at in calculator at sorry, not that, hex 55, and you look at the binary, it's just 101010. So we're just sending that with a 9 millisecond front 9 millisecond front porch, and we just do that every 1/10 of a second or so. So let's take a look again at the send message function, which is pretty simple. Most of it was just the magic numbers for the right number of ticks. So we also disable all interrupts, just like the receiver, so nothing interferes with it. And then it's since it's 38 kilohertz, 1 millisecond precision here, we just send 38 cycles for however number of milliseconds you want. Then I found that 315 ticks is 4.5 milliseconds, and then we start pulsing out our bits. So looking again at the over here, we get the 9, 4.5, and then we do a logical burst before we do the first bit. So that happens first. 22 pulses seems to be the right number there, and least significant bit first, and then more magic numbers for either the logical 1 or the logical 0 delay, and then we shift and just repeat that for all 32 bits, and then a final burst, which is shown here in the protocol, one more right at the end. And that's it for sending. So if we take a look on the oscilloscope, on the top in the red we have the infrared emitter, and then as before the yellow is the receiver, which, you know, we're just looking at that for the traces, I guess. You know, the firmware is not actually checking it. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. That works pretty well. And then we have our 4.5 millisecond, which should bring us at 1, 2, 3, 4.5. And then we have our pulse bursts. Anywhere where it's low should always be the same length. But yeah, and then we'll take a look at our logical 1, which of course is the first bit in that message. Then if we take a look at our logical 0, which is this guy right here, so it should be good. Haven't tested this on any other live equipment, but I think I think we're ready to do that. We just got to put in the right command down here and see if we can turn on the TV. Alright guys, so I haven't done a whole lot of other tweaks to the firmware. I did modify the timing just a little bit in the send message, but everything else is the same. I used the receiver to learn the commands for the TV and the audio receiver. So I'm about to actually test transmitting those out and making sure that we actually receive those commands properly. The LEDs are going to be used as well. Green will stay on for the whole sequence, yellow whenever it's waiting between steps, and it'll flash red when it's sending a command. So first thing, we're going to turn on the TV, then we're going to turn on the receiver, then we're going to wait for about 15 seconds because my DLP TV is kind of slow to start up. Then we'll change over the TV and the audio receiver to the media PC's inputs. And actually there was one other tweak I did in send message, and that is because the Samsung I mentioned earlier was either a 4 or 5 millisecond front porch. Turns out it's 4.5 milliseconds, so I just changed this to do half millisecond steps. So down here those numbers are doubled. So 9 for 4.5 milliseconds and 18 for 9 milliseconds. But anyway, I think we're ready to test this out, so I'm going to walk over to the TV, and everything should be set up. All I've got to do is plug it in and wait. You hear that? That is the sound of success.